Hi, gang. We'll let everybody get in here. If anybody has any questions, let me know or speak up. I'm going to talk about a couple suggestions and things I'm going to want to try later in the week. Let's see, 1, 2, 3, 4, 5, 6. Just want to make sure everybody gets here. So we're up to 8, 9. Okay. So this week we had the test, the first test, and the problem set. My basic thinking is the problem sets are probably going to be harder than the tests, just because there's more problems on them. The tests are still going to be designed to take you less than 2 hours, whether or not you get help with them. My only thing on the test is I want you to work alone on the tests, but I would really like it, and I don't mind, or I'm happy if you work together on the problem sets, right? because I know some of you are kind of better at the calculus or the math we're doing. Some of you are better at other things, and I think it can help you to work together. So I would really encourage you to try and work together. You know, I don't know if you guys want to set up Zoom sessions with each other or talk to each other about that, you know, either individually or as a larger group, whatever. If you know, if we were on campus, you would have the opportunity to figure that out and get together and meet in one of the library rooms or classrooms or something like that. And now you don't have that advantage, but you know, you still have the ability to get together and talk to each other about the problem sets. And you know, you guys are going to help each other and work with each other in a way that I'm not going to do, or I can't do, right? Because I'm the instructor, and you guys are going to be a little bit more comfortable doing things, trying things out together than you are and I don't know exactly how I can help you do that, but if you have ideas how I can help, then let me know. I don't know if it'll help to use the discussion board. That seems a little bit low tech to me, but a little bit kind of post and wait, where it might be better to be a little active working with each other. Right. So that's one thing I want to encourage you to do. And you know, it may make somebody, it may take somebody who's a little bit more comfortable with this stuff reaching out to everybody else rather than the other way around. I don't know. The other thing I'm going to want to try a little bit, I don't know how well this is going to work, but there's this app called Poll Everywhere. I use this with my freshman class to do polling. And even though thermodynamics is a little bit more complex than freshman chemistry or so on, I still think that we can use this a little bit. So what I would like you to do is I would like you to make an account. Make an account. If you don't have one already, you might have one already. I want you to use your u.pacific.edu email, and then what you can do is you can find my my ID, or once you get an account there, I can send you an invite, either way. But my ID is not the most convenient thing. I'm writing it down because it's hard to just know what it is. No, that's not right. (824). And then maybe on Friday I can, you know, I'll make a poll. It'll be like a quiz, right? And we can go through it, and it'll help me understand. It'll help you make sure that you're kind of understanding basic concepts that I think you should be able to just kind of make the connection to, and then maybe we can talk about a little bit, because this stuff is new, right? It's different than what you've been doing before. So I want to try that on Friday with something. So the problem sets you're typically going to have lower scores in your problem sets, but they're worth less, right? The exams are worth more, and actually you probably have a better shot of doing better on those, but you'll get important feedback from the problem sets. I think the next problem set, starting with the next problem set too, is I'll have some plotting on them. I'm sorry, the next exam, the following exams, you know, since you're going to be working on them, they're take home anyway, it actually gives me an opportunity to integrate some plotting on the tests, and we'll kind of ramp this up in complexity. We'll start with something simple, because I think that's really important. And if we have our exams, or if we have an exam that takes like 75 minutes in person and stuff, you know, you can't necessarily do the plotting, but now, because it's essentially take home, you can. Okay, so let's get started on chapter 5. Devoe. He titles us thermodynamic potentials. So what he really means here are energy expressions. And one thing that we're going to find out is that we're going to have a bunch of different energy expressions or representations. It's not just an expression, it's a function. And I'll talk about this in a few minutes about why we might want to have all these different energy expressions. Let me start off where he starts off about total differentials. We've already talked about total differentials, been on the problem set and so on. But let me give a further example of total differentials, because this kind of gets us warmed up for what we're going to do with different energy functions. Let's look at pressure. Pressure, if we think about the ideal gas equation, so if we're dealing with an ideal or a perfect gas, right, which we often do in beginning thermodynamics, then that's the expression, right? Now, if we want to do this more mathematically, we would say that pressure is a function of N, T, and V. And I would say that N is most commonly left out, and it's not necessarily that we leave N out or we're not considering, but we might say something like we have 1 mole of a gas. We're going to start allowing N to be a little bit variable. Okay, now if N is not constant, we have an open system, right? If N is constant, then we have a closed system. So this is one of those things that, you know, if the professor says, okay, we have a closed system, you have to know that N is constant, so dN is 0, right? But for now, and I think today we're going to kind of jump back and forth between having an open and closed system depending on what we want to illustrate.
Wait,
Let's
so
talk. Go
is
ahead.
dn equals 0 for a open system or a closed system?
Oh, good point. Let me change that to make it all consistent. dN is not equal to 0, right? Conversely, if we have a closed system, we would have dN equal to 0. So the times when we have a total differential, right? So I'm going to write a total differential here. The times that we have a total differential, but we don't have a dN term, then that implicitly is stating that's a closed system, right? Okay, so let's write what the total differential would be, right? The total differential, if we have a function of N, T, and P, dp by dt, and we hold n and v constant dt, plus dp by dv, t and n dv, plus dp by dn, t and v dn. So here we have an open system, right? If we're going to allow n to vary, but now we have a function of 3 variables, and I'm including n here. And Devoe is going to be describing closest, so he leaves the n out. But I want to make it a little bit more interesting and complete, right? If we use the ideal gas law, right, then we can take partials, right? In other words, the ideal gas law is analytic, so we can actually do these partials. We can say dp by dt at n and v is nr over v, dp by dv, t and n is dp, that's kind of messy, can't really read it, v, this is minus nRT over v squared, right? And dp by dn, t and v is just RT over v. So what we can do, if we have some expression for these partials, right, or if it's analytic, then we can immediately substitute in these values, right? We can say dp is nr over v dt plus, and I'm sorry, this is already a minus sign, minus nRT over v squared dv plus RT over v dn, right? So this is one thing we can do with the total differential, right? And what if we want to test to see if dp is an exact differential, right? We have the reciprocity, which basically means second derivatives taken in different orders should be equal to each other, right? Second derivatives or mixed derivatives taken in different orders should be equal, because the order doesn't matter. The order of differentiation doesn't matter. And this is the kind of thing that you should just, you can practice this, just get out some paper and start writing these things down. So what I'm going to do here, this is kind of a standard thing that that Devoe does a lot, and especially when he's doing the math. To me, it was always a little bit more confusing to hide the partial derivatives. But if you call this first one A, the second one B, and this third one C, then what we have is we have dp is A dt plus B dv plus C dn. The hard part for me, though, is that I forget what the first derivative has been a derivative of when you put the letters on. So, you can put these little subscripts, especially when we have more than 2 dimensions, more than 2 partials, more than 2 independent variables. It can be confusing and hard to keep them straight. So for example, if we ignore the dn part for a second, in other words, if we just use the example that Devoe has in the book, then what we can say is dA by dV at n is dB by dt at n, right? And again, if we just have 2 variables, then it's probably easier to remember that the A is a derivative with respect to t, so now we're going to take the v. And the B is derivative with respect to v, so now we're going to take the t, right? So let's check this out. A, right, is nr over v. So taking the v derivative of that is minus nr over v squared. And B is minus nRT over V squared. So taking the T derivative of that is just minus NR over V squared. So these equal each other. So with respect to V and T, it's an exact differential. And that makes sense if we have two dimensions. What if we have a third dimension? This makes it a little bit harder, right? So now what we're going to do is we're going to treat the n derivative, the c, right? That's the n derivative, dc by dv. And I can't do dc again, so I'm going to do db. And b is a function of v, right? So here, this gets a little bit confusing, right? Now, b is a function of v. So c is a function of n. So they have to cross each other, right? So I have to take the derivative of c with respect to the b variable, v. I have to take the derivative of b with respect to the c variable, which is n, right? And as long as I do that, I'm doing this reciprocity check. Now, if I do this, you should find minus RT over V squared equals minus RT over V squared. And in practice, if you do this and somehow include all three variables, you have to include one of them at least twice, right? In this case, we've done the B twice. Then it is an exact differential. So dP is an exact differential. Well, this is what we should find because P is a state variable. P is a state variable. And if we know P is a state variable, then we know dP is going to be an exact differential if we have written down that total differential properly, right? If it's not, then we've done something wrong in the construction of this. All right, so the next thing we want to talk about is total differential of U again. We've done this before, but what we really want to do, let me write this down. du is dq plus dw. This is very kind of generic. One of our goals is to use measurable variables in our expression. That's always the goal, right? Because we want to be able to do an experiment, measure something, and relate it to these changes. We want this to be something real, not abstract. Well, what we have is if we use PV work only, right? Then we can say du is dq minus pdv, right? So what we're saying here is no mechanical work. And also, since we don't have a dn term, we have a closed system. If we wanted an open system, we'd have to put in some sort of dn term, and we'll get to that. We haven't, because we haven't talked about exactly how to include that yet. All right, so the other thing we have is we have, from the second law, we have dq over t equals ds, right? So this is the first step in getting U kind of usable was defining our work, right? And so now we take the kind of generic dW into specific kinds of work, minus pdv. The second step, and that took a long time, this was the whole second law thing, was getting Q, dq into some terms that's useful, that's maybe measurable, or a different state function. right? Because Q is not a state function. And the whole second law thing was this culminates in dq over t is ds, a state function. So what this means now is we can say du is t ds minus p dv. So this is our first real thermodynamic potential. Because what we have now is we have put u as a function of s and v, right? From the very first thing I wrote at the beginning of the section, we would have to write u as a function of q and w, but those are not state functions, they're path variables, so that's not very useful, right? So now we've kind of attained our goal of u as s and v. Now I know before we wrote this as a function of t and v, right? And we know this makes sense because, for example, if we have no temperature change, right, then we have no internal energy change, right? So clearly internal energy is a function of temperature. It turns out, though, that for reasons that are going to be hard to understand right now, that internal energy is a natural function of entropy and volume, not temperature and volume, okay? It turns out that entropy is well-defined and temperature is not well-defined, but entropy is not possible to measure in a direct experiment, all right? So this is kind of weird. Don't want to get too into that because it's almost like a philosophical thing. Okay, what did we see before? We saw before that u is a function of t and v. So on the one hand, right, on the one hand, we had du. Now let's write it in terms of partial derivatives. Du by dt, v dt, plus du by dv, t dv. That's what we had on the one hand, right? But according to this thermodynamic potential form, right? But according to that, we have du is du by ds, v ds, plus du by dv, t, this should be s now, dv. So which is it? Which is it? Well, if you think about it, let's give a simpler example, right? What we have here is we have conjugate variables. Conjugate variables are two state variables that affect each other directly. Pressure and volume, perfect example, right? So in other words, let's say that we have some function, some energy function that's a function of volume, right? It should make sense to you that it's also going to be a function of pressure, right? Because pressure affects the volume and volume affects the pressure. Typically, we have a constant pressure system or a constant volume system, but there's some relationship between those, right? And we talked about this a little bit when we talked about enthalpy, right? Which is a constant pressure, right? I'm sorry, is a function of pressure, and internal energy, which is a function of volume, right? And these are very similar, but if there's any gases involved, then there's going to be a difference because of the way gases expand and contract, right? So we have these conjugate variables that directly affect each other. So what we can say here is that S and T are conjugate variables, right? Entropy is clearly affected by temperature and vice versa. These two are naturally related to each other in a very similar way that pressure and volume are related to each other. So even if you don't have a real solid feel for how they affect each other, you probably have at least an intuitive feel, right, that temperature increases motion, which increases entropy, and so on. So these are directly related to each other. And we call these conjugates, right? So we call them conjugate pairs. So what's the deal? We have two expressions for du that are slightly different, but what this shows is that we can express an energy in terms of different variables, right? And we may want to do this. Okay. Well, let's now take the boxed equation. Let me compare. I'll just write this explicitly. Let's compare our thermodynamic potential version of du. Du is T ds minus P dV. This is a function of S and V. So let me express now my internal energy as a generic function of S and V. That would be equation 2 that I wrote down. Du is du by ds, V ds, plus du by dV, S dV. If we relate these to each other, right, du is a state function. That means any total differential expressed one way needs to equal one expressed another way, especially in the sense of two variables. So this gives us our first differential relationship. What I mean here is some measurable equals some thermodynamic partial or slope, right? And what we find here is that T is du by ds at V, at constant V, and N, we have a closed system, but I'm not bringing N into this now. And du by dV at S is minus P, right? All right, so this means two things, that we have some thermodynamic abstraction related to a direct measurable, T and P, if we're dealing with an S and V kind of space, right? The second thing this means is, do you remember we've done some partial derivative manipulations, both on the part of the problem set and the first exam? Now what we can do, remember on the exam I defined this mu j, it's called the Joule coefficient. We've called that a partial. It turns out that that's the slope of a line, right? If you're doing an experiment, then that's just a slope. So it's kind of a measurable from an experiment. We should be able to measure that. Turns out they couldn't measure it because when they first set this up, their experiments were not sensitive enough. So basically it always read 0, but that didn't mean it was necessarily 0. Anyway, when we're doing now manipulations of these partial derivatives, we can directly substitute in these variables, right? So under certain conditions, certain partial derivatives are directly related to measurables, so we can substitute them in, and it turns our kind of expression that's full of partial derivatives into measurables, right? So this is the beginning stage of something that's very important. And that's why this requires a little bit of practice. Okay. So now let's talk about open systems. We need some dn. Well, on the one hand, in the abstract way, let me label this as the abstract way. We can say, okay, du by ds, yeah, that's right, ds at V and N. I'm going to introduce N now, right? So now when I'm doing one partial, I have to hold two other variables constant, ds plus du by dv, s and n dv, plus now this is going to be du by dn, s and v dn. So on the one hand, writing it this way is completely general. If we want to include an n dependence, all we have to do is take a partial with respect to n, right? But if we look at our potential, our thermodynamic potential, what are we going to put in here in front of the dn? What is the physical relationship or physical measurable, or what are we going to put in there? All right, so what we do is we're going to introduce the concept of chemical potential. All right, and in other words, we're going to say du by dn at constant s and v is going to be this variable mu. It's the same as the one on the test, mu j, but it's not really the same thing. This is called chemical potential. This is a kind of a weird concept, right? And it can take a long time thinking about what the hell is a chemical potential and what does it mean. I mean, temperature, I can use a thermometer. Pressure, what do I use to measure chemical potential? You really can't. There's no kind of meter that measures chemical potential. What is it? Let me give you an example of, might help you understand what chemical potential is. Let's think about something very simple, a one component system, but it's two phase. And I'm getting a little bit ahead of myself because we're not talking about phase equilibrium yet, but to me, it can help you understand what chemical potential is representing a little bit. One component, let's say this is water. Two phases, gas and liquid. And we have it in equilibrium, okay? We have it in equilibrium. So let me draw a cartoon of what this looks like. We have the liquid down here, we have the gas up here, and it's a dynamic equilibrium, right? In other words, molecules are vaporizing and condensing, but at the same rate. So there's no net change, but the density of the gas and the density of the liquid are very, very different, right? They're different by a factor of about 1,000. There's a difference of about 1,000. So in other words, the density of the liquid over the density of the gas is roughly 1,000. Okay. It's at equilibrium. What holds this there, right? What we say is the chemical potential of the liquid and the chemical potential of the gas are the same, okay? Chemical potential is something that we can measure at an equilibrium sense the same way temperature is. Okay, let me give you another example compared to temperature. I have one hunk of metal, I have another hunk of metal, two different temperatures, I put them in contact. They're at equilibrium when the temperature is the same, right? And what we're really doing, saying TDS, DS is the variable that we're allowing to change so that the temperatures are the same. dN, the composition, which the easiest way to think about this is density, right? dN is really a function of density. The number density in the gas phase is much, 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 much less than the number density in the liquid phase. But the chemical potentials are the same. And because the chemical potentials are the same, there's no net movement between the two. If the chemical potentials were different, there would be mass flow. In other words, we would vaporize the liquid or we would condense the gas until we attained equilibrium. Okay, does that make sense? So chemical potential at this point is very abstract to you, I get it. But chemical potential is going to be the measure that determines equilibrium. What's the value? I have no idea, right? What is the numerical value of chemical potential that allows us to be the same? I have no idea. All I'm saying at this point is that when we're at equilibrium between the gas and the liquid, the chemical potential of the gas and the chemical potential of the liquid are the same. Chemical potential is the thing that drives a chemical reaction. In this case, the chemical reaction is very simple: vaporization or condensation, right? But when the chemical potentials of the two phases are the same, we're at equilibrium. So chemical potential is a very, very abstract concept to you at this point, I am sure. But it is what we use, or we use to define chemical reactions, basically. So it's going to turn out to be really important. This is chemistry. We're going to do reactions, right? In some sense. So if we have S components, right? If we have a one, let me not say components, because in the example I just gave, we had one component, right? Water, but we had two substances, right? So it's one pure substance, but it's two phase substances, right? Does that make sense? So I have two substances, one component, right? So what we have to do in thermodynamics is we have to start making some distinctions. Just saying a pure substance is not enough. We have to differentiate between the phase too, and this is the language we use. So I'm defining two substances, but one component, right? So I'm using component where in other forms of, or other fields of chemistry, I might just say substance. Okay, so in general, if I have S different substances, I can write du is TdS minus PDV minus, now I'm going to have a summation over my number of components. Starting at I is going to be my label, I equals 1 mu I dni, right? So what I'm saying here up here, right, is I have the gas and the liquid. So I just have two terms, one term for the gas and one term for the liquid. And we haven't really got there yet, but what I'm telling you to help you understand chemical potential is that chemical potential is the thing that defines equilibria in the chemical sense. Okay. Hopefully that helps a little bit. Okay. All right, so what I want to do now is I'm going to take a little bit of a digression. And this is going to be the stuff that's in Appendix F for, this is Legendre transformations. What the heck is a Legendre transformation? Well, a Legendre transformation gives us the ability to change the variables of our system, right? So what if we want to have a system that is P dependent, not V dependent. U is a function of volume. What if we want some function of pressure? What is the related energy, right? What's going to happen to the energy when we transform the dependence from volume into pressure? Now, we already defined this a little bit, right? We know this is going to be enthalpy. It's going to be enthalpy. We already have a definition for that. We talked about it a little bit, right? Devoe waits until chapter 5 to talk about enthalpy, which to me is just too long. Everybody knows what enthalpy is, or you talk about it. And so to me, it was important to define it in the sense of the constant pressure heat versus the constant volume heat. So there's a bit of that in chapter 5 that I've already talked about. But what if we want to transform between the variables? And we do this with a Legendre transformation, right? We've already done this implicitly, right? Because we've been talking about internal energy so far as a function of T and V. And then I just kind of magically transformed it to a function of S and V, right? That came about by using the second law, dq over T equals ds, right? How can we do this? I'm going to do this generally, and then I'm going to do it explicitly, okay? And so I'm going to go through the general thing, and then section 5.3 does this explicitly. So let's run through this stuff. Some of this should hopefully be fairly comfortable by now. The language should be fairly comfortable because we've talked about a lot. A general function f, which is a function of x, y, and now I'm going to introduce z. I'm going to introduce 3 variables. What can we say? Then the total differential df is a dx plus b dy plus c dz, where now we can say a is df dx holding y and z constant, b is df by dy holding x and z constant, and c is df by dz holding x and y constant. So again, this is just kind of a visual simplification, right? Using this A, B, and C is kind of, I think of it as a visual simplification because it declutters the expression. Now, at this point, we could say stuff like dA by dy equals dB by dx, and that makes it a total differential. But we've done that already. I want to do something new. What I want to do is I want to define a new function g, and I want g to be a function not of x but of a. In other words, I want to transform it to dependency on the other conjugate variable, right? If I have a function of s, I want to make it a function of t. If I have a function of p, I want to make it a function of v. If I have a function of n, I want to make it a function of mu. That's a little weird, right? Because chemical potential is new and weird to us, but it's irrelevant to the math, right? How do we do this? The way you do this is you take the F, right? And we're going to subtract off the product of the conjugates. We saw this already when we did enthalpy, right? We saw this already when we did enthalpy. So the other reason that I introduced enthalpy before Devoe introduces it is because at least somewhere in the deep, foggy recesses of your memory, you've done that before, right? So when you say U minus PV and we go through the steps to get enthalpy, it's kind of familiar. So, but now this is exactly what we're going to do. F minus AX. I'm going to subtract off the product of that function. It's very important that we say we subtract off, because it's going to be a little confusing when we do this with P and V, because the term for P and V is minus PDV, right? And subtracting that off means we're going to add it. Okay, but we'll get there. We'll get there. I'm going to define it like this, right? And I said this out of order. I'm going to subtract off the conjugate product term that I want to switch. Okay. Well, what does this mean? Well, then this means let's look at the total differential. The total differential then is going to be df minus dAx. This is df minus ADX minus XdA. Okay. Now let me put in what df is. df is going to be A dx plus B dy plus C dz, but I have the other part defining G dg, right? Minus A dx minus X dA. And we see what happens here is the term, what we've done is we've essentially subtracted out the term that we want to transform. And now we can say dg is minus xdA plus b dy plus c dz, right? This is not df any longer. It is a new function. But in a way, it gives us the same information of df, just in a different coordinate system, basically, in just in a new space. Okay, so now what do we have? We have, let me write this down, dg now is minus x dA plus b dy plus c dz, right? And we have minus x is dg by dA at constant y and z. Well, the b and the c are unchanged from the f, right? So those terms corresponding to df are exactly the same. But kind of, not quite, right? Because what we're holding constant now is a instead of x. And this is the part that's more important, right? It's these things being held constant. So these two things, now a held constant. Okay. This also gives us new reciprocity relations such as minus dx by dy at A and Z equals dB by dA at Y and Z. Okay. In thermodynamics, these reciprocity relationships are called Maxwell constructions, right? So I think maybe Friday we're going to talk about Maxwell constructions, but it relates back. Maxwell constructions come from reciprocity, and reciprocity is due to the state function being a total differential. So it's all kind of related. Maxwell constructions are very, very useful. But we'll get there. We'll get there. We can do this as many times as we want. Right? We can define H. H, we could define as this is F minus AX minus CZ, right? What if we want to transform between C and Z and A and X at the same time? We can do that. DH then ends up being minus X dA plus B dy minus Z dC, right? So here we transform two variables, okay? But I want you to note one thing. When we wrote du is TdS minus PDV plus mu dN, for example, this is not a Legendre transformation. This was just fundamentally defining a thermodynamic potential or thermodynamic energy, okay? But we don't want to confuse that with a Legendre transformation. Okay, so now we're ready for the last big thing for today, 5.3, defining new thermodynamic potentials. Okay. Closed systems. Let's start with closed systems. Again, this means no mu dN terms, right? That's what that really means. Okay, so we know that U is a function of S and V, right? And as I've said, I've mentioned this at least once, that S and V are the natural variables for U, right? This will not become clear exactly what this means until later. But S and V are the natural variables. That means if we want to measure internal energy, the easiest way, the most direct way to do it is to measure the system as a function of entropy and volume. Well, volume is not a problem, but we have not figured out a way to measure entropy directly in an experiment. We always have to do it implicitly through the heat at a constant temperature, and you know, maintaining constant temperature can be difficult. So what if we want to get this into something more convenient? What if we want to get it as a function? We know this is enthalpy, T and V. Well, what we're going to do is we're going to we're gonna end up subtracting off these different things, okay? So if you think about it, remember that we defined H as U minus, now here's the part that's difficult, right? You have to subtract off the term that exists in the expression. Now, since it's U is minus PDV, we have to subtract off minus PV, like that. Right, and what this led us to was H being a function of T and P. Now, I know I've been saying that U is a natural function of S, but really, if we write it in the TDS form, then we're going to be stuck with TDS. If we write it in the partial derivative form, then we could make it go the other way. I don't want to get too much into this right now. It'll become clear when we use this. Right, this is enthalpy. We also have Helmholtz. Sometimes known as Helmholtz free energy. A is going to be defined as U minus TS, right? And we have Gibbs, also free energy. G is defined as U minus TS plus PV. So what we see here is there's some sort of simpler relationship between U and A, and H and G. So A is to U as G is to H, right? So I know you've heard of Gibbs free energy before, and we use this as a sign for spontaneity. Notice we haven't said anything about this yet. We're going to get to it. But the reason that Gibbs free energy is more known to us and seems more familiar to us is its relationship to enthalpy, right? So it's really for the same reason that we're more used to enthalpy than internal energy. We're more used to Gibbs free energy than Helmholtz free energy. But there's going to be certain circumstances that the energy we measure is going to be actually Helmholtz free energy. This is mostly when we're dealing with solids. Okay. All right. So what do we get? Let's run through the enthalpy example of the infinitesimal changes. This is going to be du plus pdv plus vdp, right? dA is going to be du minus TDS minus SDT, and dG is going to be du minus TDS minus SDT plus PDV plus VDP, right? And of course, what we're going to do is we're going to substitute in the version of du that's most convenient for us. Okay, let's see here. Now, I'm going to go into 5.4 a little bit. I wasn't really planning on doing this, but let me introduce section 5.4. the reason is because I feel like leaving it at this point it's kind of like it's almost like a cliffhanger, right? We haven't really expressed these the way we're going to use them. So let's get them to the point where we're commonly going to use them. We know that du is TDS minus PDV. If we make now these substitutions as above, right, what we're going to get is dH equals TDS minus PDV plus PDV plus VDP. So dH is going to be, we end up canceling these, TDS plus VDP. This looks weird to us, right? Because what you should do when you look at H now is you say, oh, the natural variables of H are S and P. And I'm okay with P, right? Pressure seems like a good thing to be able to deal with. But again, I'm stuck with the entropy. And this is a little bit of a problem for us. But what it ends up telling us is it tells us that enthalpy and internal energy really don't deal with entropy, right? Temperature is the measurable, right? And that's, again, this is going to be one of those things that's not super clear to you at this point, and I don't expect it to be, but that's kind of what it's telling us. So this is our second now thermodynamic expression or thermodynamic potential. If we do this for dA, we're going to get minus S dt minus PDV. If we do this for dG, we're going to get minus S dt plus VDP, right? So H is going to be a function of S and P. A is going to be a function of T and V. And G is going to be a function of T and P. Right? So depending on what variables we want to use in our experiments, this tells us what the natural relationships are. All right. Now, we also have the differential forms, right? We also have the purely differential forms of these differentials. dH equals, well, let's look at dH. ds is the first dependency, so this is going to be dH by ds at constant P ds plus dH by dP at constant S dP. dA is going to be dA by dt at constant V dt plus dA by dV constant T dV, dG dG by dt constant pressure dt plus dG by dP at constant temperature dP, right? These are the differential forms. What does this mean? This means we can relate the thermodynamic forms Now, I want to stress to you, and this is kind of important because in my mind, it makes things simpler. You should be able to write these things down from memory, right? This seems like something you would have to memorize, but there's a very natural progression. There's a very natural progression here, okay? And if you can remember, where are we here? If you can remember this, right? Everything starts from du, right? And from du to dh, we want to transform the PV part, right? So we're going to subtract, and from U to A, we're going to transform the ST part. And from U to G, we're going to do both, right? That allows you to get to these forms, right? Now these differential forms, once you know what each thermodynamic potential depends upon, you should immediately be able to write those. Just like if you had an f of xy, you could write the partial forms of that, df by dx, dx plus df by dy, dy, and so on. So especially the differential forms, you should be able to write down. What these give us, right? If we look at the H forms, right, we can see that from H, TDS is dH by ds. So in the enthalpy space, then temperature is dH by ds over P, right? So this gives us how enthalpy changes with entropy. That's temperature. The other relationship we have is V is dH by dP at constant S. Okay. So temperature and volume are things that naturally fall out of enthalpy. Using A, right, we can see that minus S is dA by dt. So the S and T derivatives are, the temperature derivative is always going to give us S. The S derivative is always going to give us T, and vice versa, right? So minus P equals dA by dV at T, right? And these come from relating the two differential forms to each other, but notice how the conjugate variables fall out of the derivative of the other conjugate variable, right? The hard part is just, if you're trying to memorize it, which again, I don't advise, right? And that might just be because I could never memorize this stuff. I could never memorize this stuff. I had to derive it. But to me, that gives you a deeper understanding too. You can look for patterns and all this stuff, or you can just kind of do it. dG by dP and T. Okay. Notice enthalpy and free energy give you the volume kind of naturally. But enthalpy gives you the temperature, and free energy gives you entropy. Okay. What we're going to find out later that both G and A may be defined purely through the second law. This is in fact the way that we define G and A, even though we don't really do it for A because we never spend any time on A, especially freshman year. But this is the way we do it in freshman thermodynamics, which you've probably totally forgotten by now, right? But freshman thermodynamics, we use the second law to define a new energy we call free energy, right? And in classic thermodynamics, we kind of do it the other way around. We define the free energy through the internal energy, and then we're going to go back and relate it to the second law. So it's just kind of a matter of whether we go from the front of the house to the back of the house, or the back of the house to the front of the house to get in the house. It's all in the same place. But this is kind of where we're going to get. Now, what I'm not going to do today, I'm going to save for next time. I'm going to do reciprocity, which, remember, we call Maxwell constructions or relations, right? So what equating the two forms of the differentials to each other, what that gives us is it gives us the measurables, right? It gives us the experimental measurables, things we're going to measure in the experiment. What the Maxwell constructions are going to allow us to do is it's going to allow us to transform between these different spaces, between the different dependencies in a backdoor way, right? And this for most people is the hard part, is if you have these thermodynamic manipulations that involve partial derivatives. Again, we've done a little bit of this so far, but it allows us to move from one space to another. In other words, it allows us to move from a partial in terms of S to a partial in terms of T and P, maybe. And we'll do that next time with some examples, because it's one of those things that you've probably never done before, and it can be a little intimidating and take some practice. Okay. So what I'm hoping to do by Friday, my aspiration is to have your tests graded by Friday. I think I can do it, but I'm not going to promise, but I think, right, because I would really like you to have those by Friday. So that's my goal, and I'll also post the next problem set too. I actually want to do that before I have your exams graded, so so you guys can move on and start thinking about that. But that's the goal. Does anybody have any questions? If you can, what I would suggest for these things is I would go ahead and try to start from the beginning of each of these things, right? Like what I have here boxed in red, and then practice writing down the differential form just from scratch, just so you can kind of see where that comes from. The differential form is almost purely mathematical, right? And maybe it'll help if you, instead of writing H to get the differential form, just use F. F is a function of X and Y and Z. What are the differential forms of that? And just practice seeing how to construct those. So when you do the differential form of DH, it's just a matter of keeping the variables straight, really. It's almost purely mathematical. But the thermodynamic potentials are more expressed in terms of the thermodynamic variables we're interested in. Okay, so today I have an office hour at 3. So I'll be here at 3 if you have any questions. Again, start thinking about talking to each other offline, however you can do that. And if there's some way that you think I can help you with that, let me know. Like I said, I'm not quite sure what might make it easier for you to do, but I'm interested in helping you do that. Okay. Okay, I guess I should stop the recording.